So I'm talking about the seasonality of the impact of high latitude stratospheric observations, particularly radiosonde observations. This is work done with my colleague Ina, and thanks to Sean and Tony for comments and suggestions. So I'm going to give a bit of background, talk about stratospheric variability, FSOI of the observations, one slide on radiosonde data denial studies, and then discuss the results, and then it's time for breakfast. So the background to this, some years ago, WMO agreed the concept of the Global Basic Observing Network, GBON. And important details were agreed in October 2021. And essentially saying that we want profiles every day at a certain spacing up to 30 hectopascals, and then a subset we want them up to 10 hectopascals. There's also a specification that the observations should be high resolution. But for over a period of 2 or 3 years, there was discussion in different working groups and so on about what these limits should be, and the density. And at one UMetNet meeting on the topic, I suddenly thought, well, I'm sure that the upper level data are more important in winter, and the rest of the presentation is looking at how true this is. This is just a slide, the current distribution status of the global radiosonde network. There's just under 800 active stations. There are gaps over the ocean and over Africa in particular. And something like 60% send medium or high resolution data now. The others send low resolution. Some still don't send buffer. And is that, move that to the side? Yeah. So stratospheric variability, these are plots of the 10 hectopascal U wind at 60 north and 60 south from era 5. And it's clear that there's things going on in the northern hemisphere. There's this huge variability in a sort of extended winter period, and then very little variability in a 4-month summer period. And it's to do with the polar vortex, and in the northern hemisphere it moves around and wobbles and splits, and the largest disturbances form stratospheric sudden warmings. In the southern hemisphere, it's a bit different. The vortex tends to be stable, except when it's breaking down in the springtime there. And so the largest variability is in the springtime there. Now, which is it for page down? I did earlier. This is the variability in U again, or different latitude bands. So at the top, we've got Northern Hemisphere 45 to 90 north. And again, this very large variability in the winter at something like November to April. In the Southern Hemisphere in the middle, you see the springtime and some indication of downward propagation over time. And one of the other things is that the influence on the troposphere is largely or just when you have these very large variability events. The bottom one briefly just shows the tropics, and there's this semi-annual oscillation there. Throughout the forecast range, this is up to day 10, you see that the large variability corresponds to larger errors, and this is true to some extent at 500 hectopascals on the right, but it's the variability and the errors are there's much more winter spring difference at 50 hectopascals. So we're getting on to impact, FSOI. It's an impact of how important different observation subsets are for short-range NWP. This is for the satellite ATMS, showing the 4 highest peaking channels, and channel 15 peaks at about 2.5 hectopascals, channel 14 at 5 hectopascals. And you can see much larger FSOI in the winter, this extended winter period, in the northern hemisphere. At the top, in the southern hemisphere, it's the winter spring period where there's a huge FSOI, and in the middle there is something of a semi-annual cycle. This is the radiosonde FSOI. So the top panel on the right, and I've split it for temperature U and V. So again, this is for pressure less than 100 hectopascals. And again, we see much larger FSOI in winter than in summer. And most of the impact is coming from the wind. The larger impact in winter is despite there being somewhat fewer observations there. That's what the green bars are about, the number of data points. And the bottom right shows that the balloons burst at lower altitude in winter. So the further north you get, the more of a seasonal burst problem there is. The main way of improving it is to use a larger balloon. And in fact, in North America, they do use quite large balloons. So the bottom left plot shows that it's mainly in Eurasia that we see this drop off in winter. This is a plot of the vertical distribution of radiosonde FSOI shown per datum. It's got maxima at standard levels, and at low levels, temperature is important. In the stratosphere, the winds are more important, but there's a particular peak around the tropicals, tropopause. And it's difficult to pick a level above which we don't want observations. In the stratosphere, the horizontal length scales increase with height. So in some ways, it's reasonable to have lower density observations at 10 hectopascal than 30 hectopascals. And then I did several data denial studies, and this shows the results against radio occultation data at T+12. This is for 20 to 90 north, and most of the impact comes from the wind. So the black line is taking out all the radius-on data. The green line is just taking out the radius-on temperature and humidity data, and that has a rather smaller impact at upper levels against radio occultation. But one of the surprising things is that the magnitude of the changes in winter on the right, DJF, and summer left, JJA, are not that different. It's slightly larger in winter than summer, but this is not
About a minute, Bruce, left. Sorry to interrupt.
Yep.
Thank you.
Not a somewhat different picture from the FSOI. So they both agree that the radiusons are more important than the radius-on temperatures in the stratosphere. And this is because satellite temperature information is plentiful, but wind information is rather scarce. The FSOI suggests that the winter impact of radius-on data is maybe 3 times the summer impact, but in the OSE, the impact is more similar. And what I think is happening is that the lower stratosphere is more geostrophic in winter, and this means that the satellite temperature data can partially replace the wind data. There's a bit more work to do on this, and any other comments are welcome. So in summary, in the northern extratropics, this stratosphere is very active in an extended winter period, and it interacts with the troposphere then. It's very quiet in the summer. The radius-on data in the stratosphere, especially winds, have a much larger FSOI in winter. Balloons burst earlier in winter, so we have less data then, unfortunately. You can use larger balloons to counteract this. The OSEs are more nuanced, and obviously the satellites give a lot of temperature information, and I think that they're helping in the winter via geostrophy with the winds, and a bit more work needed before publication. Thank you, and questions.
Thank you, Bruce, for the excellent talk. On the notepad, I see there is a question from Andrew Lorenz, who is asking whether is your FSOI total energy norm integrated over the full model depth in brackets because some systems have an upper cutoff.
That's a good question. It's pretty much the full model depth. There may be a little bit at the top that isn't. I should double check that point. Yes.
And I do not see any other questions, but perhaps one from me here. It is really interesting to see the variability of the impacts being very closely tied to the variability of the atmosphere and the stratosphere in particular here. Do you think, Bruce, that these findings can be used to inform future decisions as to more targeted launches of radiosones or other in situ systems, for example? If we have a bigger impact in the winter, perhaps this could be an incentive for different countries to release more radiosones during this period as opposed to the summer and keep the total number of radiosones the same.
Yes, that's what this work is about, to try and guide decisions about sort of how many radiosonde descents are made and also how high they go. Yes.
Thank you. There is a incoming question which is being written at the moment. Maybe I would use the time to ask a quick question beforehand. Is this variability also characteristic of other observing systems in the ECMWF? Or is it particularly for satellites and radiosones that you see the most pronounced variability?
I mean, it's in the stratosphere, it is basically satellites and radiosondes that provide the information. In the troposphere, the surface and aircraft data has a bit more impact in winter than in summer, but this is in FSOI terms, it's of the order of 10%. It's not the huge variation that we see in the stratosphere.
Okay, interesting. And I can see that this question is being just written down. It's essentially about Akira Yamazaki is asking, is the OC in the OC, did you deny U and V data for the wind against denial for T data? Two variables versus one variable.
Sorry, I didn't get that.
So he's asking in the OCE whether you deny U and V data, both of the variables for the wind, against denying only temperature data.
Okay, there was one OSE taking out all the radiosonde data, and then another taking out just temperature, radiosonde temperature and humidity. There was a third one where I just took out all the data above 100 hectopascals. In the stratosphere, that it looks much the same as taking out all the data at all levels.
Okay, on that note, let's thank our speaker again virtually, and I will hand off